Okay, so in this video, we will try to see some information about the entropy of a canonical ensemble. We know the general expression for the entropy for any kind of ensemble. What is that expression? S is equal to K ln omega. And that expression is valid for all the statistical mechanical system. S is equal to K ln omega. So that equation does not have any problem with canonical ensemble also. That system is really applicable here also. But only thing is that now we are trying to see that that expression through the spectrum of partition function. So that is the intention. Entropy of a canonical ensemble. So here we know that in a canonical ensemble, PR is equal to PR, the probability of any element to have an energy ER, PR, right? So PR is equal to 1 by Q exponential minus beta ER, where Q is the partition function of the system. So now for our convenience, let's take logarithm on both the sides of this expression, and then I can write ln of PR is equal to minus ln Q, right? I'm just taking the logarithm on both sides. So minus ln Q minus beta ER, right? Now if I take average on both the sides, why average? Because I am trying to connect some kind of a microscopic parameter like ER to a content which can be measured like an entropy. So we know that it is ensemble averages gives you the experimental information. I already proved that. So for that purpose, we take the ensemble average of this expression. So average of ln PR is equal to minus ln Q minus beta ER, right? Yeah. So this is how I do the averaging, because there is no averaging over here. It's ln Q cannot be taken. Averaging does not apply there. So ln PR is equal to minus ln Q minus beta ER, and PR is what? It's a probability, right? So the average of PR or average of ln PR is equivalent to just simply ln of PR or PR. So average of PR and PR are the same, because PR is already an averaged quantity, right? And there is no point in taking an average of an averaged quantity. Right? If I do 10 measurements and I tell you that the average result is 14, so average of 14 is again 14 only. So that is it. So that extends to any probability number. So the average of ln PR, I need not write average anymore. Ln PR is equal to minus ln Q minus this average of ER. Now I know that it is actually equal to I can express it in terms of the U, right? So minus of beta U by summation over RPR. This we have already written here, right? We have already defined that in one of our for previous videos. This was the expression. So this average U, so U is an average quantity. That's why I am not putting the average symbol for U here, because what is U? U is an average energy. So I need not now put the symbol of average over here. So therefore L minus ln Q minus beta U by summation over R PR. Okay, so I just readjust or adjust the equation by multiplying the PR over here, right? So this mathematical rearrangement, I can write it as summation over R PR ln PR is equal to minus sum over R PR ln Q minus beta U, right? But and now again the summation does not apply over Q. Summation is just applicable only to those elements having R. So summation over R PR, what is that? Summation over R PR is equal to 1, right? That's how all the probabilities, if you add together, it will be only 1 here. So therefore summation over R PR is equal to 1. Therefore I can write that expression as sum over R PR ln PR is equal to minus ln Q minus beta U. Minus ln Q, I can write that as A by KT. Why? Because in one of our previous videos we know that A is equal to minus KT ln Qn, and I can write now minus ln Qn as A by KT. So A by KT minus beta U, that is beta can be written again in terms of KT. So A by KT minus U by KT, which is equal to beta into A minus U is equal to beta. A minus U is what? A minus U is equal to minus T and minus TS, right? Because U is equal to A plus TS, therefore A minus U is equal to minus TS. So therefore minus beta TS is equal to minus S by K, right? So this is what I needed. S is equal to minus K summation over R PR ln PR, right? So this is the expression which I am getting. S is equal to minus K summation over R PR ln PR. Now based on this I know a couple of information. So what is the value of entropy for a system at T is equal to 0 Kelvin? At T is equal to 0, what will be my entropy? That will be 0, right? So entropy will be 0 at absolute 0 temperature. Therefore, I can now write, based on this expression, S is equal to, T is equal to 0, S is equal to 0, which means that for S is equal to 0, so what was my equation number? 2, 3, 4, 6, let this be 7. Based on 7, if S needs to be 0, the necessary condition is that my ln PR needs to be 0. So at what condition the ln of some quantity will be 0? When that quantity will be 1, which means that my PR is equal to 1. At PR is equal to 1, only then I will get S is equal to 0. So the PR is equal to 1 means there is only one state. There is only one microstage for the whole system. Whole probability is in that one single energy, right? So, which means that at t is equal to 0, this expression, as expected, indicates a system that the system is settled down to one single state, and we call them as the ground state. That state as the ground state. So that is the beauty of this expression. We are able to connect whatever things we did, all the assumptions were correct. This is what it's proving. And again, what will happen at some high temperature? So this was the situation at T is equal to 0 Kelvin. PR is equal to 1. At high temperature, what will happen? At high temperature, my system is expected to occupy different energy levels, because there will be energy distribution which will be initiated by the temperature. Therefore, my PR value will get smaller, right? Because now the particle which was there is going to be distributed into more number of energy levels, right? So more number of energy levels means the probability of a particular energy level to have is getting reduced. So therefore my PR gets smaller. So from the expression 7, what does that tell you? PR gets smaller means my ln of PR will get, so PR is having a value between 0 to 1, right? Which means that the PR is going to have a fractional numbers. So the PR gets smaller means my ln of PR is going to have higher negative quantities, right? Smaller fractional number means logarithm of that quantity will have higher negative quantities. But in this equation, we have a negative over here also. So negative, negative, positive. What happens ultimately is that my entropy is going to increase. So that is actually what we expect also. As the temperature increases, S gets increased, which is really following according to our expression. The entropy gets bigger as the temperature gets bigger. So that is it. So that is about the general about the entropy of a canonical ensemble. So that is it. So we have given a basic overview of the partition function and its general behavior and the entropy of this canonical ensemble. So in the next video onwards, we will take some practical, some situation, some example where we will try to evaluate its partition function according to its conditions. So now we know the importance of the partition function. Now our attempt should be to calculate or evaluate or derive the partition function for as many systems as possible. So for that purpose, I will help you in deriving the partition function for a couple of systems. That we will start doing in the next video.